Hello again, everyone. This is the second part of the second lab on work and energy. And in this part of the lab, we're going to investigate conservation of mechanical energy. So let me give you sort of the basic idea here. So we have the cart again, and in this case, it's going to be launched with a spring. I'll just show you this. So I have a pin in here, I'm going to pull the pin. It's going to launch it and it's going to go up the track. So something like that. And what we can do, I have a photo gate at the initial position. So right when the spring is fully extended and it's reaching its final velocity from the spring, I want to measure that velocity. So again, if I know the diameter of this metal post and I know the time that it takes that little metal post, the diameter to pass through the photo gate, then I can get a good estimate of that initial velocity. Okay. The other thing is, I know that initially the cart has some potential energy, right? If I choose the table as my reference, so the table is 0 potential energy, I can measure with a ruler, and I just need to pick some consistent spot on the cart, so I'm going to use the bottom of this little vertical line here. I can measure that relative to the table, and then that will allow me to calculate the potential energy relative to the table. And then when I launch this and it goes up to the highest point, I can stop it at the highest point, catch it there. And then what would the kinetic energy be at the highest point? Well, if it's instantaneously at rest, right, just for an instant, then the kinetic energy must be 0, right? Because remember, kinetic energy is 1/2 mv squared. So the velocity is 0 just at that instant. But it still has potential energy. In fact, it has more potential energy than it did initially because it's at a higher point now. So again, I can measure that distance from the table up to the bottom of that line, and that will allow me to calculate the potential energy. Now, if we assume that all the forces are conservative, there's no friction acting, we're assuming the friction is very low here, then what should be true is that the mechanical energy, which is the sum of the potential energy and kinetic energy, should be conserved, right? So if I calculate, actually it's at any point throughout, right, the motion. If I were to calculate the kinetic energy, I'd have to know the velocity at this instant, calculate the kinetic energy. If I knew the height, the potential, that sum should be constant throughout the entire motion. So in particular, I'm going to compare the mechanical energy at the beginning, because I know the potential, and I know the kinetic because I know that velocity, and compare that to the mechanical energy at the highest point, which is simply just the potential energy, right? Because the kinetic energy is 0. And hopefully, those two mechanical energies should be very close to one another. In theory, they should be exactly the same. There's going to be some error. There probably is a little bit of friction here. It's really hard to determine the exact highest point of this cart, but hopefully those mechanical energies will be similar to one another. Okay, and that's sort of the basic idea of this part of the experiment. Thanks.